In our project, we're going to be discussing the forces that a dam submerged into a river water feels. This is an example of a sketch of a cross-section of a dam. And let's first name the basic components here and add a coordinate system, so it is going to be easier to talk about the objects that will appear in your projects. So the first thing that we have to set up is the bottom profile of the river, and we're going to call that bottom profile B of x. Now, what is a B of x? B of x is a height of a river bottom or an elevation of a river bottom with respect to some coordinate system that is potentially far away. So we're going to draw it here on the side. So this is going to be my x coordinate. This is going to be my y coordinate. We're going to call this y coordinate elevation. The idea is that in our project, all of the vertical axes are going to be elevations of an object above the sea level. The x coordinate has a less important meaning. In some sense, it is just a distance across the cross section, but it doesn't have a special. The origin 0 doesn't have a special meaning. So. But still, we needed to be able to discuss objects in calculus. So B of x, the bottom profile of a river, is the distance at any point x from the sea level to the bottom of the river. We're going to have some additional components. We're going to also talk about water level, which again is going to be an elevation, meaning it's going to be measured from some sea level point, and we're going to name that YW. And we're going to have the leftmost point, which we're going to label as Y left, X left, and X right as well. But more importantly, we're going to talk about the width of the entire dam. So that sets up the basic components of our sketch. Notice that the water level is constant. It is at a constant elevation, but the depth of the river itself varies. The depth of the entire river is the distance between the water level and the river bottom. Okay, so now it's time to start talking about the physics. We're going to localize ourselves to one small patch of the river, and in particular on the point in its center, and we're going to give that point coordinates xi and yi. This is going to play the role of our test approximation object, and we're going to call it a test volume in this case. But compared to our previous calculations when we were dealing with volumes and areas, this is not going to be a rectangle, but rather a square. And so when we perform our integration, we're going to be sliding that square in all directions until we cover the river, the river cross section, and that's how we're going to be forming our integrals. So we are going to be interested in several quantities associated with this river profile. First, we're going to be interested in the area submerged underneath the river. Then we're going to be interested in the total force that the river feels, and the total force is going to be important because that total force will have the ability to displace the river to displace the dam horizontally. So this is sometimes also called the linear force, as opposed to rotational force or torque, which instead of displacing the dam horizontally, is going to rotate it around a point called the fulcrum. In calculating the structural stability of the dam, both of these forces are going to be important, and so we're going to calculate the both of them. The source of this of both of these forces is the hydrostatic pressure. The hydrostatic pressure is the pressure that the column of water exerts on a certain point that is submerged underneath the water. So if I have this location xi and yi, then the hydrostatic pressure P at that location xi, yi is going to be given by rho g h. Oh, I'm sorry, rho g, we're going to label this last quantity d. Rho is the density of the water, g is gravitational acceleration, and d depends on yi and is the depth of that test patch underneath the water. So it is the distance between the elevation yi distance between elevation yi and the elevation of the surface of the water yw. Pressure, or the hydrostatic pressure here, is the force divided by the area on which it is acting. Vice versa, if we want to go from the pressure to calculating the force, we have to integrate the pressure over a certain area in order to add them all up and to obtain the force. So this is, in our case, what we are going to do. What we are going to be calculating here is the force, and we are going to we will want to add all of these little test patches together. So in the spirit of what we were doing in class, we're going to think of this as, and actually let me change, we're going to think of this as a sum of pressures at location xi, yi against the area of this little patch delta A, and summed against all indices I. So we imagine that we don't have just a single patch here, but that this I index runs from 1, so maybe the first patch would be somewhere here, x1, y1, and that we would basically grid up this entire dam and sum then the contribution of the pressure times the area, which means contributions of forces against all of these quantities. Now, what is the area? What is the area of this test object? As before, we're going to introduce a delta x and delta y. I say as before because I'm referring to the class. So like in class, we're going to introduce quantities delta x and delta y, which are going to represent the width and the height of these little test patches. So when we multiply pressure by the area, we get a unit of force, and then when we add all of these forces up, we get the total force on the dam. Now here, notice I'm writing pressure as if it was a function of both position and position in the horizontal direction and the elevation, but notice that actually pressure depends only on the y-coordinate, meaning that the pressure against any horizontal, that the pressure on test volumes that are on the same depth is going to be the same. This is the reason why the book prefers to first integrate this force F against the horizontal axis, where it doesn't change, and then integrate against the vertical axis, effectively adding pressures along every one of these strips. To go from pressure at to go from force on a single point, which is this, force at a point, to torque at a point, we have to discuss how the torque is created. Now, if I'm looking at the object sideways, this is my dam, and my test patch was somewhere, let's say here. And here I have calculated that I have a certain amount of force acting on it. P of xi yi times delta x delta y. So this is the force. If I simply add these forces up, I would get the total force on the dam. But if I want to calculate the torque, I have to account for the fact that the torque is force times the arm against which this force is acting. So what is an arm? To introduce the arm, we have to have some point around which this rotation happens. That is the fulcrum, and that is a point around which all this object will rotate. So when the pressure is squeezing the point at the location yi, vertical location, and we have the fulcrum sitting at some point yf, then the distance between the point at which the force is applied and the fulcrum is called the arm of the force. And we're going to denote it here as R. Now, as you can tell, R is again going to be a function of yi, but not of the xi in our case, and I will explain why soon. So if I'm looking at the dam here, this is the sideways look at the dam, whereas this would be the frontal look. If I'm thinking about, again, force acting on our test strip, if I'm trying to compute the torque that results that force, from that force, meaning the torque that's going to be toppling the dam in or out of the screen, I have to establish a line of the fulcrum as well. And this fulcrum distance is going to be at a constant elevation for us. And in fact, we're going to place it exactly to lie at the minimum of our bottom profile. Why is that? We imagine that the entire area of our dam acts as one solid object, not as individual vertical strips, meaning that that solid object has a single hinge around which it is rotating, as if you are opening a flap of, of a bag, for example. The entire flap of the bag hinges along a line that is a hinge, and in this case, our entire dam is going to hinge against a fulcrum line that lies somewhere in the land beneath it. And for the sake of this problem, we're going to imagine that that line exactly matches the lowest point of the entire dam. If this wasn't the case, if fulcrum was allowed to change as we move the x point left and right, then we would be interpreting the dam as if it was composed of vertical strips, and each of those vertical strips would rotate around a different point. Okay, so to calculate the torque, we're going to perform the similar approximation as we did before. We're going to be adding the force, which is P xi yi times delta x times delta y. This is my force, multiplied by the arm of the force, r of yi. Now, I, on purpose here, do not write what r of yi and d of yi are for our calculation here. In this case, this distance here to the red line here is going to be r of yi. I don't know why I wrote here d as a function of xi. D is a function of yi as well. So these two quantities, the depth and the arm, are going to be varying only with respect to the location of the test patch, but not with the location x, simply because we're going to imagine that both the surface of the water and the fulcrum are flat constant lines of the constant elevation, and so the only thing that could change d and r is how high or how low we placed our test object. Of course, we're going to place it everywhere when we're integrating, but when we're developing the integrand, the function that is going to be integrated, we imagine it as being steady at a one spot. So we have these two calculations.